Septic bricks.
Now, the thing about multiplication when you're dealing with vectors, you actually have a couple different kinds. You have the scalar multiplication, then you have what's called a cross product that we'll look at later, and you have what we're going to look at today, which is dot product. Okay? Now, dot product, the way it's actually referred to, because you have these multiple multiplications going on, they refer to it as just dotting two matrices together. Okay, rather than multiplying. So, as far as the operation goes, it's very, very simple. All you do is multiply the corresponding pieces and add them up.
That's not what we're trying to do yet.
Okay? So if you have two vectors, xy and xy, you just multiply the x's, multiply the y's, add the two things together. Okay? So when you do that, what's your result going to look like? Is it going to give you a new vector? No, it's just going to give you what? Some single number, right? So the way I equate it, scalar multiplication you have in both matrices and in vectors. You just distribute whatever value to everything out front, right? If you do the cross product stuff we'll look at later, that's kind of like when you multiply two matrices together. You get a new matrix. Can you think of anything with matrices that when you do that operation, you end up with a single number representing that overall matrix?
Yeah.
The what? Well, not quite. I'm talking about a single number that tells you something about the matrix that you use for other things later. Starts with a D.
Oh,
Discriminant.
yeah.
Not discriminant.
No,
I'm
that's
just
not it.
thinking of
It's, what is it? Yeah, determinant?
Determinant.
Yeah.
It's a determinant. Dot product for vectors is kind of like determinant is for matrices. Okay? It gives you a single number that you then use as a property of those two combined vectors. Okay? Now, because of this, because you're getting a single number and all you're doing is multiplying and adding, you have some basic properties that work. It doesn't matter if you do u dotted with v or v dotted with u. They give you the same thing. If you dot the zero vector with any given vector, well, it's going to be 0 times x plus 0 times y. It's just going to be 0. If you're dotting with v plus w, would generate a new vector, right? So either you can dot with the new vector or you can dot them individually and then proceed to add those two together. So it acts as distribution over addition. Okay? One of the more odd properties that can be useful at times is if you dot any vector with itself, it actually gives you the magnitude squared. Okay? And lastly, the thing is when you dot two vectors together, if you have a scalar multiplier, it's kind of like if you're multiplying 2xy, you don't actually distribute the two to both things because it's multiplication. You distribute over addition, you don't distribute over multiplication. This is the same idea. You have a scalar multiplier out front, you don't distribute over the dotting of two vectors. You can either dot the first or dot the second, you can't dot both. Or you can multiply by the scalar for the first, multiply by the scalar for the second, but you can't do it to both. Because it wouldn't make any sense to have this be equal to 2x2y. You could either have 2xy or you could have, technically you could have x2y if you like. Either one of those, but you couldn't have it to both. Okay? It's just a general example of what you can and can't do. So, actual operation-wise, this is fairly easy. All I'm going to do, if I'm dotting these two vectors together, I'm going to multiply the x's. So 3 times 2 plus 4 times negative 3. What am I going to get? 6 minus 12 gives you negative 6. There's your answer.
Well, so what do we use the dot product?
We'll do that in a second. What's the next one? Yeah, you get 2 minus 2, 0. Lastly? They are a type. They're a type of grouping symbol, yeah. The fact that they're this indicate that they're vectors with the origin, with the initial point on the origin. That's that component form stuff we did from yesterday, right? Yeah, and the day before. What do you get for the last one? You said?
-8.
Yep, -8. Okay. Now you can combine these concepts together as well. You can see what I was even writing for part of that. Okay. If I have the three vectors, u, v, and w, if I want to find each of the following. Now, u dotted with v times w. Well, what would u dotted with v be? 18, because you're going to have negative 6 plus 24. So then what am I going to do with the 18 out front? Distribute it. You multiply times both parts.
18 and negative 18.
So you generate a new vector that's 18, negative 18. For U2W, so the vector U, and you have 2W. Now you got a couple options here. You can either deal with the 2 now, or you can move it out front and deal with it later. What do you want to do? You can deal with it now. Go ahead, Jeez.
Could you just distribute 2 to 1 and 1?
Yep, that's what we're going to do when we deal with it now. Okay? So, I can distribute that scalar multiplier now to get 2, negative 2, and then proceed to dot the other 2 together. So what's that going to end up giving me? Negative 2, because you're going to have 6 minus 8, so negative 2. Not too bad? Okay. What if I had a dot product of U with itself is 7? So they've already done the dot product. They're not telling you what U is, but its dot product is 7. Then what is the magnitude of U?
7. No.
Square root of 7. Yeah, it's just let's straight out the properties. So this is what this is saying is if I take U dotted with U, okay, that equals 7. Well, U dotted with U is the magnitude of U squared. So that means the magnitude of U is just square root of 7. Say it again.
We can't, you don't want it.
I would just leave it as that. There's no reason to give the decimal, honestly. Okay. Now, another way to find the angle between two vectors, and this is that shortcut that I was talking about. Okay. Rather than having to get them both on the origin, find the angle between them, and then interpret what those two angles, or the individual angles, and interpret what those two individual angles would translate to, you can actually just use the dot product for this. Okay. If I want the angle between two vectors, I can actually just take, and the reason is because you can figure out that side, but that's why it's working. U dotted with V divided by the product of their magnitudes, it will always equal the cosine of theta. That theta being the angle between U and V. Okay? With that, I can then just do inverse cosine and generate theta. This is one of those you want to memorize for formulas. Okay? So, if I have these two vectors, if I want to find theta, I'm going to set up cosine of theta is equal to these two vectors dotted together. What do I get when I dot those two vectors together? That is 0. Yeah. 3 minus 0 is just 3. Or plus 0, whatever. On the bottom, what do I have? The magnitude. So I'm going to take the square root of 3 squared plus 0 squared. Which is just what? 3. Square root of 3 is? Or the square root of 3 squared, I should say. On the other one, 1 squared plus 6 squared. Square rooted? Square root of 37. Then simplify that, you get what? 1 over the square root of 37. And if I want theta, well, I'm going to do something with it, so there's no reason to rationalize it. The denominator. Inverse cosine. So when I do inverse cosine of 1 over the square root of 37, I get what? Say again?
80.54.
Yeah, 80.54 degrees. And if you stop and look at it for a second, if I actually graph these two things, you have the vector 3, 0, and you have the vector 1, 6. Does that make sense that that would be an 80-degree angle?
Yeah.
Yeah. Okay. Now, you can have a few different results that come up because of this. Okay? Whenever you're talking about the angle between two vectors, you have 5 different ways it could work. You can either have an obtuse angle, Obviously, if you're somewhere between 0 and 90 and 90 and 180, you could have the vectors be in opposite directions. In other words, you have 180. As soon as you pass this 180, what's going to happen?
They're going to be an error or something.
No. It's going to change back to something like this. Because now instead of measuring this way, you just measure the other way. If I put this just a little bit further, you then start measuring this. So those max out at 180. Okay? Which is good because inverse cosine is always going to give me a result between what?
1 and 180.
Yeah, well, 0 and 180, yeah. You can also have where they're the same direction. If you get a theta value of 0, they're literally on the same line. And you can also get 90 degrees. Okay? Now, thinking about this formula back here, how would I know that this is 90 degrees? Just looking at that fraction. How would I know theta would have to be 90 degrees just from the fraction alone? What?
Cosine 90 is 0.
It's 0.
Okay. So that fraction, what would make it 0?
If the top was 0.
The top is 0. In other words, if you have two vectors and you dot product them together and you get 0, what does that mean the angle between them is? They're perpendicular. Or the book will actually use the term orthogonal. Orthogonal means this, roughly the same thing as perpendicular. It actually refers to multiple dimensions. Okay? So, for instance, if I literally have these two lines that are perpendicular to each other, since I'm recording, I should probably do this over here. If I have two lines that are perpendicular to each other, okay, I have a third vector here that's going off in this direction, so to the left. Well, that's perpendicular to the vertical, but it's not perpendicular to the horizontal, right? Well, I can also come straight up out of the page into 3 dimensions. That's why the term orthogonal means basically perpendicular to everything. Orthogonal is actually referring to like this, and we'll get into that more with 3 dimensions, but that's why the book will use the word now. Okay? And we will get into 3-dimensional vectors later.
This chapter?
Not this chapter, later on. But what that means is I can do a very quick check to see if things are 90 degrees to each other. All I have to do with these two things is what? Dot product, and if it equals 0, yeah, so I'm just going to multiply the negative 12 times 5/4 and the 30 times a half. What's negative 12 times 5/4? Negative 15. 30 times 1/2? So what's that mean? Yeah. Therefore, yes, these are orthogonal. Or U and V or whatever.
What are those 3 dots?
Therefore.
Yeah, it literally just means therefore.
Is there like a shortcut to writing orthogonal? Or
Not really.
Honest.
If you want to write perpendicular, you can, as long as we're not talking 3-dimensional.
So you know how like you can like display perpendicular with like an upside down T? Could you add in like the diagonals to make it look like 3D and call it orthogonal?
Well, I mean, yeah, you could go like this, I guess.
Yeah.
Draw an X, Y, Z axis.
I'd rather just write it.
Yeah.
Just call it thog.
Fog.
Okay. Questions on any of this stuff so far?
Yes.
Okay, I'm going to cut it off there. We'll get into some a little bit harder stuff with this dot products and some of the manipulation of it on Tuesday. Quiz is when?
Monday.
Monday. Make sure you're ready.
Monday.